the last video for Unit 10, and we are going to put together some big concepts that we've learned and do some more practice with logarithms and exponentials. You're even going to master the ability to do all of these things, which is pretty incredible. First one, more with exponentials and logarithms. We are solving for x, which we are going to start by saying, can I rewrite 8 as a base of 2 or 2 as a base of 8? Why, yes, we can. 8 is the same thing as 2 to the third. So that is still going to be raised to the 1 minus 2x equals 2 to the first. And then power to a power I'm going to multiply. So 2 to the 3 minus 6x equals 2 to the first. Now because I have the same base, I get to just look at my exponents. I'm going to subtract the 3, divide by the negative 6. X should be equal to 1/3. The other way to do this is to take a log of both sides. Let's say you didn't see that you could rewrite it that quickly. I'm going to take a natural log of 8 to the 1 minus 2x equals the natural log of 2. Power property says I can move this whole exponent down to the front. Divide by the natural log of 8, which in your handy-dandy calculator, natural log of 2 divided by the natural log of 8. It's 1/3. You might be saying, but Ms. Schwartz, our answer was 1/3. How can that side alone be 1/3? Well, watch the math magic begin. If I subtract 1, I now get negative 2/3, 1/3 minus 1 whole. Then I'm going to divide by negative 2, which is really the same thing as multiplying by a reciprocal. 2's cancel. Negatives turn positive. X itself is equal to 1/3. All right, this next one says to graph and find the domain, asymptote, and intercepts. So we have a natural log parent function, and we are adding 2 on the inside, which means we are going to go to the left 2, and we are adding 3 on the outside, which means we're going to go up 3. So I'm going to start by plotting the natural log function, which I remember from previous lessons, always goes through the point 1, 0, and through the point E1. Now I'm going to take that curve, and I'm going to move each important point to the left 2, 1, 2, and up 3, 1, 2, 3. I'm going to take this point, which was E. If I go back 2, I'm going to be at about 0.78-ish, and up 3, 1, 2, 3. If I take this vertical asymptote and I move it to the left 2, dotted line's not working so great, I get my same graph that has been transformed. That should not be touching the asymptote, running along it. So our domain here, if I were to squish all of this purple curve to the x-axis, I'm going to end up with my domain being from negative 2 to infinity. My asymptote is a vertical asymptote at x equals negative 2. And, to find the intercept. Intercept. I'm going to set y equal to 0. That'll let me find the x-intercept. And then I'm going to set x equal to 0. That'll help me find the y-intercept. So this side, I'm going to subtract 3. I'm going to get rid of this natural log by e-ing both sides, or rewriting as an exponential. E and ln is going to cancel out. X plus 2. Looks like my x-intercept is going to be e to the negative 3rd minus 2. So to write that as a coordinate point, e to the negative 3rd minus 2, comma, 0. Because y was 0, that's how I started this whole process. My y-intercept is going to be a little bit easier. Y equals 3 plus the natural log of 2. And that's it. In went 0, out came 3 plus the natural log of 2. And of course, you can get decimal approximations for both of these, but exact answers are always acceptable. Graph and find the domain, asymptote, and intercepts. So I want you to do this one just like we did on the last, except I'm going to have you notice that your parent function this time is not the natural log. It's the natural exponential, e to the x. Our key features then are going to be a horizontal asymptote at y equals 0, going through the point 0, 1, because anything to the 0 power is 1, and going through the point 1, comma, e, because e to the first power is e. So take that these pieces of important information and graph your parent function, and then see if you can perform this transformation. Go ahead and pause the video and try on your own. Here's my transformed function in red. Moved it to the right 3 and down 2. Well, my domain is still from negative infinity to infinity. That hasn't changed at all. My range, if it asked for it, is no longer 0 to infinity. It would be negative 2 to infinity. My asymptote is now at y equals negative 2, because we've shifted down 2. And my intercepts, just like on the last one, I know from my mathematical definition, to find an x-intercept, I set y to 0, and to find a y-intercept, I set x to 0. Go ahead and clean up those answers, and let's compare intercepts. Pause your video. Ms. Schwartz, these numbers look so familiar. The natural log of 2 plus 3, and e to the negative third minus 2, but wherever have I seen those in my past? Yes, well, in this previous example, this number was our x-intercept, and this number was our y-intercept. And yet in this example, we changed locations, x-intercept and y-intercept, which means what must be true about this function and our function on the previous page? You are right. They are inverses. Their x's and y's have completely switched locations. And if you were to graph them on the same coordinate grid, hopefully you would see and you would notice that we have reflected. Here I have drawn our purple graph from the previous slide and put it with our red graph, and you can see that they are a reflection of each other over the line y equals x, which is our inverse relationship. All right, find the domain of the following. Well, we know the domain of a log function of just the parent, log base b of x, is that x has to be greater than 0. Well, that means that whatever's inside of our logarithm must be greater than 0. Kind of like when we had square roots, we could be greater than or equal to 0. So I'm going to solve x3 is greater than 4x, which means that 3/4 is greater than x. You could also see that as x is less than 3/4. If you write that in interval notation, negative infinity to 3/4 not included. This one's going to create a little bit different of a situation. First of all, we want to say whatever's on the inside must be greater than 0 because of our log parent function. Okay, so then to solve this, I don't just multiply both sides. This is a rational inequality, so I need to find my critical numbers. Critical number of x equals 1 because that makes the numerator 0. Critical number of x equals negative 2 because that makes the denominator equal to 0. I'm sure this is ringing a bell at the end of Unit 8. Plot on a number line. Pick some test intervals. So a number between negative infinity and negative 2. I'll choose negative 3. And if I plug in negative 3 on the top, I get a negative 4 over a negative 1, which creates a positive number, which makes that a true statement. If I pick a number between negative 2 and 1, I'm going to go with 0. I get negative 1 over positive 2. And that ends up being a negative, which is not greater than 0. Then if I pick a number from 1 until infinity, I'll choose 2. 2 minus 1 is going to give me 1 over 4, which is positive. And that does fit our greater than 0, which means our domain is going to be all the ones that came out positive or true in this case. And 1 to infinity for our domain. So yes, things we have learned in previous units are important for our current unit. What? Okay, expand the logarithm. This one I'm going to leave you to try on your own. We've done a lot of these in class. So you want to expand using your product property, your quotient property, and your power property. So pause your video and come back when you are all set and ready to check. Check it, see how it went. Make sure you rewrote that square root as a 1/2 power and brought that down in front. But this should be your expanded logarithm. Moving right along. Evaluate. Ooh, Interesting, because I want to just like cancel that. I'm just like, cross that off. But I don't really know what to do with this plus sign here. So I'm going to think back to some other exponentials that I've worked with. If I had, with polynomials, x to the 2 plus 4, that would have come from having x to the 2 times x to the 4. So okay, yeah, that could help me. So this could be 5 log 5 of 6 times 5 log 5 of 7. Because rewrote with the base, show the base twice with product, creates the addition, so like that's working for me. And now I can cancel this, and I can cancel this. And I end up with 6 times 7, which is 42, which I believe is the answer to the universe. Or I could also combine this into a single logarithm. So this is going to be 5 log 5 of 6 times 7 because of this addition property. Now 5 and log 5 can cancel. We still get 42. Right? This one again is going to be a time for you to try on your own. So go ahead and solve this logarithmic equation. A hint would be to condense to a single logarithm first. Pause your video. Kind of an unusual number, but we do end up with x equals negative 13/31. And because I started with a logarithm, I need to go back and check for extraneous. So if I do 7 minus negative 13/31, that's going to turn positive. We're good. If I do 3 times negative 13/31, I don't really know what that is off my head. 3 times negative 13 divided by 31, negative 1.25 plus 2. Now I'm in positive territory. So that works, in which case this is an okay answer. It is not extraneous. The last thing I want to talk about is not in your notes packet, but it's really, really important for your finance project. Just our investment problems, we've done a lot with this equation. And we've done a lot with basically plugging in all of our different pieces and finding A. And that's not really that hard, it's more arithmetic, right? It's not that it's the algebra that's going to get us, it's really just plug and chug into our calculator. But I want to remind you that now if I had this equation and I asked you to solve for t, so let's say I had 300 equals 150, 1 plus a 6% rate monthly to the 12t. You could divide by 150, which is going to be 2. In your calculator, you could figure out what all this is. Let's go ahead and do that. 1 plus 0.06 divided by 12, 1.005. And now if I wanted to solve for t, ignoring the fact that this was an investment equation, if I need to get something out of the exponent, I need to take a log of both sides. And then that power property, I don't like those parentheses there, that power property allows me to bring that 12t down to the front. So to get t by itself, I need to divide by 12. I also need to divide by the natural log of 1.005. And what I get for a t value then, so what did I say? Natural log of 2 divided by 12. Then I need to divide that by the natural log of 1.005. I get t equals 11.58. And t was representing time. So what this really means is this is the time that it took for my account to grow from $150 to $300, or in this case, the time to double. And there's a rule in economics called the rule of 70 that allows you to find the time that it would take for something to double, and it's based off of the natural log of 2. So those of you that take econ, you will maybe recognize that rule of 70, and it comes from this type of situation with the fact that inevitably you're going to have a natural log of 2 because you got to get this exponent down in front. So remember, you have a lot of power, pun intended, in our exponential unit for how you solve these things. That's it. Unit 10, it's done. Congratulations.